talking about our first reaction of the semester, right? Because up until this point, we've only been talking about purification techniques or identification of compounds via melting point. But in this case, we're actually finally talking about a reaction. So we'll be discussing the conversion of tert-butyl alcohol to tert-butyl chloride via an SN1 or a nucleophilic substitution reaction, right? So here you can see an example of how a nucleophilic substitution reaction works. You have your substrate, it's bound to this atom, whatever it may be, and you have a nucleophile which has free lone pairs for bonding. They can be negatively charged or not. It depends on what kind of nucleophile it is. And so the reaction takes place. The nucleophile attaches itself to this, usually carbon, right? Because it's organic chemistry. And then you have a leaving group, which was this original X, right? Okay, so here are some examples of nucleophiles. R stands for carbon. This is probably one of the strongest bases. There are a variety of different reactions that cover this kind of carbon. We also have negatively charged amine species, which is also a pretty strong nucleophile. Negatively charged oxygen species, any halogens, halides, ammonia, or any amine, right, with a carbon attached to it. And as you can see right here, or even alcohol can serve as a nucleophile. So nucleophilic substitution reactions can happen in one of two ways. You can see here there's SN2 and SN1. Now, what does this mean, right? So the N in SN stands for nucleophilic, and of course the S is substitution. You always want to write your N little. This is just convention. This is telling you the rate of the reaction, right? Whether it depends on one or two of the compounds in the reaction. So a bimolecular reaction is an SN2 reaction, and the rate is proportional to, which is what that means, right? To both the concentration, which is denoted by these brackets, of the substrate, and the concentration of the nucleophile. So in other words, it's a bimolecular, right? In an SN1 reaction, the rate of the reaction is proportional to the concentration of the substrate, and only the substrate, which makes that a unimolecular reaction. So other than the definitions, what are some other differences between an SN2 reaction and an SN1 reaction? Well, to start off, you have here the SN2 reaction reacts with mostly primary carbons, right? So you have a carbon, right? You have two H's, right? And then whatever your leaving group might be. In this case, I'm going to put X. So these SN2 reactions prefer these kinds of carbons, right? That are primary, meaning there's only one bond to carbon. Versus SN1 reactions, they prefer tertiary carbons. So it would be a carbon that's bonded to 3 other carbons, and whatever your leaving group is, right? In this case, X again. Now, what other differences are there? Well, one other thing I need to mention is that a secondary carbon could go either way, right? SN2 or SN1, depending on the reaction conditions. So what other differences are there? You see here, SN2 reactions typically require very strong nucleophiles, so something with an anion, right? As we saw in the one of the previous slides. Whereas an SN1 reaction can easily happen with a weaker nucleophile that's neutral. SN2 reactions occur mostly in polar aprotic solvents versus SN1 reactions which occur in protic solvents. The reason for this is because you form a carbocation, right? And this carbocation is actually stabilized by the protons, right? So this is the reason why SN1 prefers protic solvents. SN2 reactions require a good leaving group. You'll see a table in your textbook or wherever that shows you which ones are good leaving groups, right? But this one also requires a good leaving group. as well. In fact, I think this one even probably requires it more so than the SN2 reaction. With SN2, one important thing to note is there's always an inversion of configuration. So if you start off with an R, you end up with S, or vice versa. With SN1, since you form a carbocation, which is the next point here, you get a mixture of S and R, depending on, well, it's a pretty much even mixture, right? Because the carbocation forms, and then the nucleophile can attack from either side of the carbocation. Again, SN2 reactions don't form carbocations, versus SN1, which do, which causes this to happen, the racemic mixture. And this is a concerted reaction, meaning it happens all at once, right? And the SN1 reaction is a 3-step reaction, so it happens stepwise. So the synthesis of tert-butyl chloride is an example of an SN1 reaction, right? Basically, you have your tert-butyl alcohol here, and you put it in HCl. The OH detaches from this carbocation, or tertiary carbon, to form a carbocation, and then the Cl is easily able to get into this tertiary carbon to form tert-butyl chloride. So one very important thing about organic chemistry is knowing the mechanisms of reactions. It helps you better understand what is going on during a reaction. So here you see your tert-butyl alcohol, and you end up using these lone pairs, and they grab onto this proton here, right, from the HCl, and you end up forming what's known as an oxonium ion. This is a fast step, right? Okay, so, but then in the next step, you end up forming your carbocation. And this is a slow step, which makes it the rate determining step, if you remember from your general chemistry class. So now that you have your carbocation, and here the geometry isn't really right, but it's not focused on that in this slide, but this is actually going to be a trigonal planar, right, with an empty orbital. So the next step is the attack of the nucleophile. So here you have your chloride from HCl, and it attacks onto this carbon. Now, this won't form a racemic mixture simply because this carbon has all methyls around it, right? But if you didn't have all the same around the carbon, you would have a chiral center, and it would probably form the two different chiral centers, right? The R and the S. And here you can see another example of the mechanism. This shows you some more clearly what's actually happening. So you have the formation of the oxonium ion, which, as you can see here, is an equilibrium, right? So it can go back and forth between this and the oxonium. And then so is the next step, right? The removal of the water to form the carbocation. It can be reversed by having this water bond back to the carbon. Now this next step is irreversible because you have a chlorine bonding to the carbon, and this is not a very good leaving group, right? The chlorine. Versus, say, iodine, which would be a much better leaving group because of the size of the electron cloud. So one thing to note here is that tert-butyl alcohol is water soluble, and this is why, right? Because we have this hydrogen bonding. OH is able to be dissolved in water, whereas tert-butyl chloride doesn't have hydrogen bonding, so it's not soluble in water, not very much. This is also important to note. This is not a redox reaction because you'll see here, tert-butyl chloride, you have chlorine, which is more polar than carbon, and here you have oxygen, which is also more polar than carbon. So there's no change in polarity here, right? So continuing on this topic, right, what we see here is that the rate depends on the oxonium ion concentration, right? So this is because it's an SN1 reaction, right? And the rate of the reaction depends on the concentration of the substrate, not the chloride, which is the nucleophile. So the ease of this alcohol reaction, it would be from tertiary to secondary to primary, meaning the easiest to alcohol to react in this manner is a tertiary alcohol. And this is mainly because alcohol is a difficult leaving group, right? One other thing to say is that the reactivity of the halogen acids, the most reactive is hydroiodic acid, and then HBr and then HCl. Now, I said earlier that iodine is a good leaving group. It also happens to be a very good nucleophile, right? So it's able to attack the carbon more easily than, let's say, chlorine. Yeah. Tertiary alcohols are able to react with any of these acids, even at room temperature. So the chemicals needed for this reaction are listed here, right? We need hydrochloric acid, of course, as the source of the nucleophile. The tert-butyl alcohol, its IUPAC name is 2-methylpropane-2-ol or 2-methyl-2-propanol. This is actually more IUPAC. This is more of a conventional way of writing it, right? Because it's easier to pronounce. You need 5% sodium bicarbonate, and you need anhydrous calcium chloride. So one important tool in this experiment is the use of a Pasteur pipette, right? You can see here is a glass pipette with a bulb, right? And then here's a plastic pipette. I personally prefer glass pipettes. I guess it depends on the procedure, right? Some things eat away at plastic. You don't want to use plastic, right? One thing to know is that with these glass pipettes, this is reusable. This gets thrown into the glass waste after being cleaned, but you don't throw this away because we reuse these. These are disposable, right? The plastic pipettes. So as always, it's important to know the safety of these experiments. Always do your experiments in the hood. Always wear your gloves and goggles, right? Concentrated HCl is not a very nice chemical. It can burn you very quickly. It also produces fumes, and you don't want to inhale that. It'll irritate your lungs and probably damage them pretty severely. So always watch out for these things. Be informed. Don't do any stupid or dangerous things while working with these kinds of chemicals because they can really hurt you badly. So the experiment goes as follows. You take a test tube. You add your 15 milliliters of concentrated hydrochloric acid. And then you add your tert-butyl alcohol here. You might notice if when you do this experiment, there will be layers. That's not something you want. You want to make sure that the reaction happens right. So you're going to have to mix it. So what the steps for mixing the pipette? You have to first keep the tip of the pipette under the liquid and draw the solution into the pipette and then lift up the pipette and squirt it back down. Keep the pipette in the test tube at all times, right? You don't want to spill any HCl or product. Keep repeating for 15 to 20 minutes. This is your reaction, right? This is happening during these 15 to 20 minutes. Your compound is reacting. Allow the mixture to settle into two layers. The upper layer is the small layer. It'll be the tert-butyl chloride, your product. If you don't see any upper layer, you would let us know, right? If we were actually doing the experiment. The plastic pipette, again, as I said, it can be disposed of in the blue container for anything contaminated with chemicals, right? That's where all that kind of waste goes. So once that time has passed, the 15 to 20 minutes, your reaction should have gone through. The next step is to remove the HCl from your product. You take your pipette. As it says here, the glass pipette has probably better control. Put it all the way down. One trick is try not to get any of your product into the pipette. You could just add a little bit of pressure to the bulb to avoid getting any of that in here. All the way to the bottom and take out the aqueous layer, right? The HCl. you just have to be very careful, right? Because it's a strong acid. This is disposed of in the aqueous layer, in the aqueous waste, right? So, but you might want to consult with your TA prior to doing so. You might have to dilute it before you put it into that waste container. So the next step is the workup of your reaction. You want to wash it with at least 3 milliliters of water. This is to remove any acidity, right? Water is the best way to remove acidity from things quickly. It doesn't do it a complete job, but it does a pretty good job. But the next step will take care of all the rest, right? So you add your water and you do the rinse, the squirting technique, right, that we mentioned in the previous slide, just to wash the organic layer here. And then you remove the water with the pipette in the same way as previous. So this next step is to completely neutralize any acid that was left here. So this is why we add the 5% sodium bicarbonate. This is a very careful technique because it'll be very bubbly, right? You want to be very careful with that. It's actually CO2 being released from the sodium bicarbonate, right? Because it's getting acidified by whatever may have been left in the residual organic layer. Wash it, of course. You want to wash it the same way. And then finally you remove the sodium bicarbonate layer, the aqueous layer, in the same way with the pipette. So next is another wash of water. Again, all the same techniques, right, for washing, the squirt technique. And then you take it out in the same way. Why is this wash? It's to remove any of the sodium bicarbonate that may have been left behind. Since this isn't a very strong reagent, it needs to be removed, right, to get a purer product. But this is not as dangerous as removing the HCl. Because the sodium bicarbonate neutralized the HCl, right? But it's actually not as harmful. This is basically baking soda, right? So up until this point, our product has been exposed to a lot of water. Typically, you don't want water in your product in any organic reaction. So the next step is drying. So we use anhydrous calcium chloride. This is an excellent technique for removing water from any kind of organic product, right? So you want to put the calcium chloride into your test tube, and then, yeah, so then it'll become a dry product. So the next step is to transfer your organic product into a round bottom flask. You want to be careful here. You don't want to pick up any of the calcium chloride. You just want your organic product. So you use your pipette, transfer it, and you have this round bottom flask with your product in it. And the next step is a distillation. Here you can see how this distillation will work. You have your heating mantle or heating well, as it's called here. Yeah, this is what's known as a short path distillation. You have this tube right here, right? This is open to the air. You have a thermometer in here. It goes down below this hole, right? Your distillate should be here. Now, this slideshow shows a specific way you can do to condense your vapors with a test tube. I remember when I did it, I actually did it by putting ice on the outside here. I guess either way works, right? You just want to make sure you have your product that's being distilled off. And here you see another image of this short path distillation, right? A slightly clearer image. You have here your thermometer in here, with the thermometer adapter attached to this tube right here with the elbow. I know this looks like a cork, but it's not. It's actually open to the air. This is what's known as a Kleisen adapter. You have your 25 ml round bottom flask. Of course, always remember when you're using these kinds of glasswares, you don't want them to get stuck together. You also don't want your vapors to come out, so you have to grease everything, right? All the joints. As I mentioned earlier, this tube might not be cold enough to condense your liquids, so you can use test tube filled with ice. The thing is that this can form water, right? So this is the reason I think that when I did this distillation once, we used ice on the outside instead of putting the tube in, right? As you get a higher chance of getting your product in here without any water in it. Because, right, we just did a purification technique to remove water. This could possibly add water to the product again because of the condensation from the air. And with any organic or any reactions in chemistry, generally, you want to know all this information, right? The molecular weight of your compounds and the molecular and the density. So you can see here's a calculation for figuring out tert-butyl alcohol, how many moles you used. See, you have your 5 milliliters. You take the density of tert-butyl alcohol, right, 0.775. You multiply it by the volume, the milliliters cancel, and you get your, and then you divide by the molar mass, right? So that the grams cancel, and you get your moles of tert-butyl alcohol that you used. Then you check HCl, 15 milliliters used, multiply by the density to cancel out milliliters. You get your molar mass here, and you divide by that, and you get how many moles of HCl you used. Now, of these two, the smaller number is the limiting reagent, right? And so this is what you use to get your theoretical yield. So if you use 0.05 milliliters moles of tert-butyl alcohol, your theoretical yield would be 0.05 moles of the chloride, tert-butyl chloride, right? And then you just do the same but reverse to get how many grams of, or you don't even need to do that. You can actually do the same reaction forward, same calculation going forward with tert-butyl chloride as these to get how many moles of tert-butyl chloride you got. And you divide the actual yield by the theoretical yield, multiply by 100, and you get your percent yield, right? Which is right here. In this case, with these particular numbers, because say you got 2 grams of tert-butyl chloride. So that's basically it for this procedure. Please let me know if you have any questions.